Good morning everyone. Today I am going to present our final year project, bone tumor detection using deep learning. Bone tumor is one of the most dangerous cancer because it is very difficult to detect in its early stages. When detected early, the 5-year survival rate is drop 80%, but it spreads to other parts of the body. Its survival rate drops below 27%. This massive difference in the survival just because of early or late detection is what motivated us to build this project. We wanted to create an automated system that can help doctors detect bone tumor faster, more accurately and more reliably. Our system takes a plain bone X-ray images as input and automatically classifies it either normal tumorous within 0.12 seconds, faster than blink of an eye. The doctor simply uploads the X-ray through our web application and system immediately display the result. With confidence percentage, no specialized hardware is required. Any computer with internet access can use it. The current challenges in medical diagnosis is that bone tumor classification relies heavily on manual analysis of medical images by radiologists and pathologists. This approach has several times like time consuming and subjective, high expertise required, risk of misdiagnosis, limited accessibility, growing demands, etc. Currently, doctor detect bone tumors by manually examining bone X-rays images. This has three major problems. First, it is time consuming. A radiologist has to carefully examine every X-ray, which takes significant time. Second, it is subjective. Different doctors can give different options on the same X-rays. Studies show that radiologists disagree on both lesion diagnosis in up to 30% of cases. Third, in many rural and remote areas, trained radiologists are simply not available. Patients in these areas have no access to expert diagnosis. These three problems together can a situation where bone tumor is frequently detected too late. Our project directly addresses all three problems using AI. These are the datasets we have used in this project. Let me now walk you through how the system works using the block diagram. Step 1. Data collection. We collected more than 8,000 images, X-rays that publicly available from Kaggle bone cancer detection dataset divided into normal cancerous classes. Step 2. Data split. The data is divided into 80% of training, 10% for validation and another 10% for testing. Step 3. Pre-processing augmentation. Every image is resized to 224 by 224 pixels, converted to RGB format and normalized. Training images are additionally augmented with flipping, rotating and zoom to increase diversity. Step 4. TensorFlow data pipelines and optimized data pipelines handle shuffling, patching, caching and prefetching to maximize training efficiently. Step 5. The learning model, which is heart of our system. And step 6. Model evaluation, flash web applications and final classifications output as tumor or non-tumor. Our proposed architecture is a hybrid model combining two powerful deep learning frameworks. The first component is EfficientNet BO, a pre-trained convolution neural network developed by Google. It was originally trained on 1.2 million images. From the ImageNet dataset, we loaded this model with those pre-trained weight and keep it completely frozen, meaning we do not change any of its weight. It acts as powerful features extract, identifying edges, textures, shapes, structural pattern in the bone X-ray and producing a 1280 dimensional features vector summarizing everything it did. Second component is our DenseNet inspired classification head. This consists of two dense layers, one with 124 neurons and one with 512 neurons connected by skipping connections. Skip connections work by concatenating the output of each layer with the original features, ensuring no information is lost as it passed away through the network. Finally, a single sigmoid output neuron produces a probability score between 0 and 1. The score is above 0.5, the image is classified as tumor. Below 0.5, it is classified as normal. We evaluated our system on 872 balanced tested images and achieved the following result: 94.2% accuracy, 93.8 precision, 94.5% recall, 94.1% F1 score, and 96.8% AUC ROC. This key advantages here is our recall of 100 actual cancer patients. Our system correctly detects 94 to 95 of them. Missing a cancer diagnosis is far more dangerous than a false alarm. So, highly recalled is the most critical metric in diagnosis. Compared to our baseline, CNN, which achieved 88.6% accuracy, or a hybrid model improves performance by 5.6 percentage points across all matrices. Our system currently has three limitations. First, it performs binary classification, normal or tumorous, and does not identify the specific type of tumor. Second, it has tested only one dataset and need validation across multiple hospitals. 3. The system does not yet provide visual explanation of why it made particular prediction. To summarize, we have built a hybrid deep learning system combining EfficientNet, B0 and DenseNet that detects bone tumor from plain X-ray images with 94.2% accuracy, deployed as a real-time web application accessible without any specialized hardware. In the future, we have planned to extend this, classify specific tumors, subtypes, and grade CAM visualization to highlight tumor region on the X-ray validation on longer multi-hospital datasets and converted the model to a mobile application for point-of-care diagnosis in remote areas. We believe this system has a genuine potential to assist doctors in early bone tumor detection and ultimately to save our lives. Thank you.